Today we are going to discussing about floating point addition and subtraction. During this floating point addition or subtraction, we are using two floating point operands. One is AC accumulator and another one is accumulator register and another one is BR register. So for addition and subtraction, we are using the two operands that are one is accumulator register, another one is B register. After the addition or the subtraction, result will be stored in the AC register, that is accumulator. So the sum or the difference is formed in the AC. In this algorithm, we can divide it into four consecutive parts. First part is used for check for zeros. And second is align the mandisas. And third one is the perform addition or subtract operation on the mandisa. Then fourth step is normalize the result. So this algorithm containing four steps. First one is check for zero, second one is align the mandisas, and third one is add or subtract the mandisas and normalize the result. A floating point number is 0 cannot be normalized. So if the floating point number is a 0, then it cannot be normalized. Then if the number during the computation, if the result may also be 0. So some case after subtraction the result may be 0. So in that case we can't normalize this 0. So instead of checking for zeros during normalization process, we check for zeros at the beginning and terminate the process necessarily. So normally we are checking for zeros during the normalization process. Here instead that we are checking here, initially we are checking the zeros. If there are zeros are there, then we are terminate the process if it is necessary. Then second step is alignment of mandisa. So alignment of mandisa must be carried out prior to the operation. So if before addition of or subtraction operation, it will perform the operation alignment of mandisa. After the mandisas are added or subtracted. So first step is check for zeros. After that check for zeros, we are checking that alignment of mandisas. After completing the alignment step, we are perform the addition or subtraction of mandisas. After completion of addition or subtraction operation, the result may be unnormalized. So we need to normalize the result. So the last step is normalization. Here this is the algorithm. There are four steps are there already explained. First step is for check for zeros. So this portion is used for checking the zeros. And second step is alignment of mandisas, that is take place here. And next is addition or subtract operation, that is done here. Addition and subtraction operation. Then last one is normalization. So there are four consecutive parts in a floating point addition or subtraction operation. Then first step, check for zeros. First, this is the check for zeros operation. First we check that if BR, that is B register, is equal to 0. If B register equal to 0, then the operation will be terminated directly. Here, if B is equal to 0, then operation is directly terminated and the value what is the result? The result would be, there are two operands are there, only AC and BR. Then if BR is equal to 0, then what will be the result? After addition, only the content here will be in the AC. So during the subtraction, if AC containing 5 and BR containing 0, adding, after adding, the result will be 5, that is content in the AC. If a subtraction operation, the result will also 5, that is the content in the AC. So if BR, the second register, that is B register, is 0, then the result, the program will be terminated with the result in the AC. So AC containing the result. Then next case, second case, if AC is equal to 0, that is first BR is not equal to 0. First case, BR equal to 0, then we will containing the result AC, and operation will be terminated. If BR is not equal to 0, then what will be in the next step? We are checking that if AC equal to 0. If AC equal to 0, if there are two operand AC and BR register, here assume that AC is equal to 0 and BR containing the some values. So assume that is 5. So here BR, first checking that BR is equal to 0 or not. Here BR is equal to not 0. So we will come to here. Then check that if AC is equal to 0 or not 0. Here AC is equal to 0. So what will be the result? The result always in the accumulator. So we transfer the content in the BR to AC. So after addition, the content result will be 5. So that is in the AC. And if after subtraction, the result also will in 5, that is in the AC. So we are changing the content BR to AC. So BR will be contain transfer, move the content in the BR to AC, that is 5 in the BR, that will be given to AC. And the operation, we are checking that if there are two operations are there, either floating point addition or subtraction. If floating point addition, the operation is floating point addition, then this will be 5, that is a positive number. So we will end the operation. Otherwise, if the operation is a subtraction, that is AC minus 5, so the result will be minus 5. So the sign will be changed. 5 will be the previous of that operation, 5 will be positive. So after the operation, 5 will be negative. So we will, if the operation is a subtraction, then we will change the sign of that accumulator, that is result will be containing in the accumulator. Then now its accumulator sign will be changed to complemented, that will be stored in AS. So here now it's minus 5. So then it will be terminate the operation. So this is the, any one of the input is 0, then output will be like this. Then next case, if AC and B are not equal to 0, both have non-zero values. If AC and B, here BR is not equal to 0, AC is equal to not equal to 0. So both are non-zero values. Then next step is align the mantissa. So he need to align the mantissa. For that, here we are considering, so here we use a magnitude comparator. So in this second step, you use a magnitude comparator to attach to exponent. Here A and B, these are the floating points numbers. So A and B represents the exponents. So a and b are the exponents, and here we comparator means magnitude comparator means that compare the magnitude of the exponents. So there are three cases are there. If a equal to b, otherwise a is greater than b, or a less than b. So we compare the magnitude of the exponent terms of two numbers a and b. Then if a is equal to b, both exponents are equal. If the two exponents are equal, we go to perform the arithmetic operation. That means it either perform the add or subtract operation. But if the exponents are not equal, here either a less than b or a greater than b, then that is, if the exponents are not equal, the mantissa having smaller exponent is shifted to the right. So here a less than b, which one is smaller? That is a. So this a is shifted to right. That is HR, SHR. SH means shift. R indicate shift to right. So a is smaller one is a. So a mantissa having smaller exponent, that is a. A has the smaller exponent, so that will be shifted to right, and the exponent is incremented by 1. So if both, we are comparing the both exponents, so one exponent is smaller, so we are shift the that number smaller exponent mantissa part, and shifted to right means the is exponent will be incremented by 1. Then here a greater than b, here's which one is the smaller exponent part? B. So the b content of the mantissa content of b is shifted to right. SHR indicate shift to right. So b content is shifted to right, and the exponent b indicate the exponent value, so that will be incremented by 1. This will be continued up to which position? A equal to b. That is, both exponents this are equal. This process is repeated until both the exponents are equal. So this is alignment. So any one is if a exponent of that two numbers are different, then we are shift the mantissa smaller exponent mantissa part will to the right, and exponent will be incremented by 1 in each step and repeated until the exponents are equal. When both are equal, it perform the addition or subtraction operation. Here addition or subtraction mantissas. Mantissa addition or subtraction is take place here. So here we are take the addition and subtraction of two mantissas is identical for floating point addition and subtraction algorithm. Here the magnetic part is added or subtracted depending on the operation, the sign of the two mantissas. So if it is an addition or subtraction, it depends on the sign of the mantissas. AS indicate the sign of A register, BS indicate the sign of B register or BR register. Here it perform the sign XOR operation. If for addition operation, consider the addition operation. If both signs are same, if both signs are same, then XOR will be 0. Output of the XOR gate will be 0. If both are 0, then perform the direct addition operation. If A is equal to 5, B is equal to 6, both are positive number. So positive number means we are directly add this number. So here the magnitude part is added or subtracted depending on the operation. Here the operation is uh, if the sign of the and the sign of the two mantisas, if the both signs are equal, that is if during the addition if both signs are equal, then XOR gate output will be 0, then we have performed the direct add operation. During the subtract operation, if both signs are dissimilar, then it perform the add operation. A plus B will be performed and result will be stored in EA. If during the add operation, the sign of the both numbers are dissimilar, then it perform the this operation. Here also during the subtraction, if both signs are equal, it perform the same operation. Here what will we do? During the subtraction, we have find the 2's complement of B. 2's complement of B is calculated here. Then that result will be added with accumulator and the total result will be stored in the EA register. So this is the subtraction operation, and here this is the addition operation, and this operation will be result depends on the sign of the two operands, that is AS and BS. After addition operation, if the E content here, if the E content is 0, then that means E containing the overflow occurs, the magnitude are added here. During when the magnitudes are, when we are adding this magnitude, then an overflow occurs that will be stored in the E register. So any operation, if an overflow occurs, then that will be stored in E register. So when an overflow occurs, it is transferred to this flip-flop E. Then if E equal to 1, here what happens? If E equal to 1, if E is equal to 1, here performs that bit E is transferred to A1 here. Here what will be happen? That is E is content of E is transferred to A1. Here E is content of E is given to A1, and all the bits in the A will be shifted to right, and the exponent must be incremented by 1 to maintain the correct result. So then it will be ended. The operation will be ended. This process is known as normalization. Then during the subtraction operation, if the magnitudes were subtracted, the result may be 0 or may have an underflow. Instead of overflow, it may be, during the subtraction, it may be an underflow. So if the magnitude is 0, so if we consider E is equal to 1 or E is equal to 0, so E is 1 means there is an underflow, then we check that if mantissa is containing A, or if it is 0. If the 0, then we consider the entire floating point number in AC is made 0. Then end the program. So there is an underflow, then A, content of A is also 0, then make that entire floating point number in AC make 0, then end the procedure. Otherwise, the magnitude is not equal to 0. That is, it must have at least one bit that is equal to 1. Then the Mandisa has an underflow. So it has at least one bit, then it has an underflow. Then in that case, the MSB bit in the position A1, check that A1 containing the MSB bit. So that is even for that is 0. Then in that case, the Mandisa is shifted left, SHL. SHL indicates shift to left. So A, Mandisa will be shifted to left and the exponent will be decremented by 1. And this procedure is repeated. And check that if the bit in A1 is checked again and the process is repeated until it is equal to 0. When equal to 0, it will end. When A1 is equal to 1, the Mandisa is normalized and the operation is completed. Before that, when E is equal to 0, then we will complement the A and 2's complement of A is find out and AS is equal to a sign of the AS is changed or complemented. So if E is equal to 0 means there is the number is not over for underflow. After the subtraction of the result E is equal to 0, then we are just complement the result to find out the 2's complement of the result and sign will be complemented. And after that we are checking that content of A is equal to non-zero. If A is non-zero, then we are check the A1. A1 is containing the result in the E. So if E is equal to 1, then we directly end the procedure. Otherwise, A1 is containing 0. There is some leading zeros are there. We need to normalize that. So we shift the accumulator content to left and decrement the exponent. Then until there is a A1 becomes a 1. Then we will end the procedure. This is the normalization. So here no underflow may occur, then in that case base the original Mandisa that was not shifted during the alignment was already in the normalized position. Then that's all about floating point addition and subtraction operation.